Thank you, and thanks for inviting me to come here. Yeah, so this is going to be a talk about two areas that I like a lot. So proof complexity, which is computational complexity, and SAT solving, and also sort of how they interact with each other. So, let's start by making sure we're on the same page. This is what we're going to talk about, the satisfiability problem. So we have variables, they should be set to true or false. And then we have a bunch of constraints on these variables, where, for instance, the constraint x or not y or z just means that x or z should be true or y should be false. In order for the constraint to be satisfied, in particular, bar is negation. Okay, and now, of course, we have these anding them all together. So we want an assignment true or false to the variables so that all constraints hold simultaneously. And the question is, given a formula of this kind, a formula in conjunctive normal form, is there a satisfying truth value assignment? Or is it always the case that however you set the variables, some constraint must fail to hold? And since we're computer scientists, we want to know whether there's an efficient way to solve this problem using computers, right? And so you might say, well, sort of why do we need to spend time on even discussing this? We sort of already know the answer, right? And so we could have a 1 hour and 20-minute break and try out the piragi that you're offering instead. But because this is the archetypal NP-complete problem. It was proven NP-complete by Steve Cook in 71. So we know that means that it's most likely totally intractable. I mean, a standard assumption underlying many other complexity results is that, in fact, the best algorithm for SAT has exponential time complexity. So the only thing that sort of remains is, annoyingly, we don't know how to prove this, but it's sort of a standard, accepted assumption. So this is a hard problem. There's really nothing we can do. Okay? End of story. Except somehow our colleagues on the applied side failed to sort of take notice of what we were trying to tell them, that this problem is really hard, so they insist on solving it in linear time. And they're actually doing pretty well, especially during, since the late 90s, there have been amazing improvements in performance by several orders of magnitude, to the extent that today, there are SAT solvers that are solving huge industrial instances, and we're talking millions of variables. So these are truly huge instances, and sort of the way the applied SAT people think about SAT, they look at some hard problem, and they don't know what to do with it, but if they can somehow reduce it to SAT, then they're home. That's that's the end, because then they're home, they know they have a good SAT solver, and that's the happy ending of their research. Okay? So which is sort of, for me as a complexity theorist, makes me slightly uncomfortable. Because this is supposed to be a hard problem, of course. So there are two comments I should make. Firstly, that one intriguing aspect of this is that if you look inside the very best solvers today, these amazing solvers solving instances with millions of variables, they're fairly simple. So they actually are based on there's a lot of smart optimizations, but at the heart, they're really based on simple methods from the early 60s that we will talk about later. And of course, NP-completeness didn't quite go away. I mean, you can also, if you're evil, then you can cook up, an instance with maybe 100, 150 variables that is totally beyond reach, even for the very best solvers. Okay?
It's sort of unfair to say it's based on methods just for the 60s. Of course, DPLL is the 60s, but there's flaws learning.
No. There are later optimizations, definitely. Yeah. Yes, I totally agree. But at the heart, you have the DPLL method, as we'll get to in a little while. So it's, yeah. And by the way, so thanks for the comment, and it goes without saying that please interrupt at any time with any comments. I mean, the point of this is not, I guess, me getting through my slides, but having an interesting discussion about this. Yes?
These tiny formulas that are beyond reach, how are they constructed?
I'll maybe try to say a little bit about this also.
But just immediately take some other NP problem like factoring or whatever and try to convert or
that won't give quite a small, the blow up will add, that might land you with a very hard instance with say maybe 1,000 or 10,000 variables or so. But typically, random 3 SAT will, then you're down to maybe 500, 600, 700 variables, 800. It won't bring you down to 100. Random SAT with 100 variables is still easy. or within reach. Yeah. So if you want to be really evil, you want to do something smarter than random set. But it's a good comment. Yeah, random set definitely, I mean, it will scale exponentially. But if you, then on the other hand, if you know that random set is your input, then you should do things that I won't be talking about today at all. There are like special purpose algorithms that are very, very good for random k-set built on these buzzwords like survey propagation and, you know, belief propagation and whatever.
So what would be the tiniest formula to build beyond reach? Factoring is what I would have come to my first attempt.
Yeah. Let me maybe tell you, you know, yeah, I'll touch on it a little bit later. So I don't want to be thrown, you know, completely off course on my third slide. So anyway, so okay. So, but this is for me as a theoretician, and this raises a question. I mean, okay, so we have this stark dichotomy that sometimes, you know, you solve instances with millions of variables, sometimes 100 variables is far too hard. You know, how can this be? What are these set solvers doing? Why do they work so well, and why do they sometimes miserably fail? Okay, how do you analyze these set solvers? Turns out that this is something that the practitioners really don't know how to do. It turns out to be hard. There's so many, you know, smart heuristics and so much black magic. So pretty much the one thing we can do is that we can look at, okay, what are their methods of reasoning? It's somehow underlying any algorithm, it's somehow reasoning about the formula, right? And you can view the trace of a successful execution is in some sense, you know, a record of my reasoning to reach the conclusion I reached. Okay, this you can view as a proof of unsatisfiability or satisfiability, okay? And then you can analyze what method of reasoning was used, and that brings you to proof complexity. So that's where proof complexity comes in. And that's sort of, I'd say, the most successful tool to date that we have for actually analyzing these algorithms and see what they can do. Okay? And so what do the best current set solvers do? Well, as some already said, the best ones are built on so-called conflict-driven closed learning. And that really corresponds, so let me tell you, conflict-driven closed learning, and I'll tell you what it is. Then sometimes on top of this, you add some algebraic reasoning. Sometimes it's good to have geometric reasoning to be able to count, reason about cardinality constraints, like at least 5 out of these 8 variables are true. Sometimes people try to do even extended resolution, and I'll get to that. And how do we analyze these methods? Well, we can use proof complexity. So what I intend to do in what remains like a little more than an hour of this talk is to give you a crash course in proof complexity, okay? With the focus on things that are relevant for set solving. Okay, so you know the state of the art is conflict-driven closed learning. That corresponds to using the resolution proof system, which is a very well-studied proof system. Okay, then if you also add algebraic reasoning, turns out this corresponds to the way they do it. It corresponds to sort of Gröbner basis computations. There's a proof system for that. It's called polynomial calculus. And then if you want to do these cardinality constraints reasoning or more generally reason in terms of linear inequalities, that's called the pseudo-Boolean solving, and it's captured by the cutting planes proof system. And then towards the very end, depending on how we're doing, I might have a slide on extended resolution, but as I'll get to them, there's really not much we can say about extended resolution. But what I want to do is to tell you sort of on the theory side what's known about these proof systems, what questions have been studied, what answers have been found. I'll try to talk about some sort of theoretical benchmark formulas that we use to establish typically these lower bounds. And these theoretical benchmarks will also give you examples of formulas that are often hard in practice. Okay? And so just 2 caveats. I mean, it's you know, in any survey you have to be selective. I'm focusing on these proof systems. Of course, proof complexity is a rich area and many other proof systems are studied. I'm picking out these 3, resolution, polynomial calculus, and cutting planes, because they somehow seem to be relevant for set solving. There's a lot of other research on other very interesting systems that I won't talk about at all. And even for these 3 proof systems, there's sort of a selection of what results I'm going to mention. So, you know, apologies in advance for everything that I'm omitting. And also, I'll try to focus on, you know, telling the story, telling you about the results. If you're really interested in who proved what, there's actually, these slides will be online. At the very end, there are like full references for everything. Okay? So yeah, so we'll talk about resolution, and probably more than half of the talk is actually going to be about resolution, because it's like a very well-studied proof system. And then in the second half, maybe I'll talk more about these stronger algebraic and geometric methods of attacking SAT. So this is sort of the plan.
Can you just explain again, how will these different pieces connect to this success of the empirical success of satisfiability? I mean, you're making that connection and trying.
Yeah, I won't. Okay. Yeah, so I won't be, I guess, explaining why the SAT solvers are so good, because in some sense that's a great open question and nobody really knows. But what I want to tell you about is sort of our theoretical understanding of the methods that they use, and this theoretical understanding can also sort of inform you what they cannot do, and also sometimes, we'll get to it later sort of, but there's also the interesting question like, okay, so if you know, for instance, that your SAT solver is based on resolution, say, then you sort of know that if something is super hard for resolution, then it will probably be super hard for you. So okay, but you're willing to live with that. But then you could say, okay, but suppose that it's actually easy for resolution. I mean, there is a short, nice resolution proof. Can you find it? So you want to be efficient, benchmarking against your proof system. Okay, and that's a very interesting question, like how well are the best CDCL solvers doing compared to what they, the best they could, if you look at the resolution proof system. And this is also an intriguing area with somewhat contradictory results. I mean, there are some results sort of saying that well, CDCL is pretty much doing anything that the resolution can do, but then there are other results. I mean, that's a theoretical result, and then it somehow doesn't quite match what we see in practice. So that's sort of, this will mostly be a proof complexity talk, but it's going to be informed by sort of SAT solving considerations, and I'm trying to make some connections and describe, sort of hand wave a little bit about how the algorithms work. But it's mostly proof complexity. So. Anything else? Okay, good. Let's go. So we already talked about CNF formulas. Just to, here's the notation. So a formula, CNF formula is a conjunction of clauses. Every clause is a disjunction of literals. Literals are variables, or negated variables, negation denoted by bar. And let's consider clauses and formulas as sets. So we really don't have repetitions. We don't care about order. And we mostly, throughout this talk, I sort of, unless stated otherwise, I'll assume all formulas are KCNF formulas. So all clauses have bounded size k is some constant. This is mostly for simplicity of exposition. It's sort of, it makes some of the results cleaner to state. It usually doesn't affect anything. There's one crucial area where it does affect things a lot, but I will tell you. And also, if there's some capital N flying around somewhere on some slide, unless otherwise stated, it's typically the size of the formula. So the total number of literals counted with repetitions. Because that's how we're going to mention our complexity results in terms of formula size. Okay, so let's look at the resolution proof system. So we get a CNF formula, and in resolution we want to prove, so notice which is sort of the hard case. If you want to prove lower bounds, the hard case is sort of the unsatisfiable case, because the SAT case, then you need to find a satisfying assignment, and then you have it, it's a short certificate, it's really nothing you can do. So the hard case, and where you can prove lower bounds, is if the formula is unsatisfiable, and you need to sort of prove that out of the exponentially many satisfying assignments, none will work. That's sort of the hard case. Okay. So the resolution starts with the clauses of the formula, and I'll refer to them as axioms. And then we just derive new clauses by applying the resolution rule, which says that if I previously derived C or X and D or not X, then by case analysis over X, I can derive C or D. Okay? And then I just apply this rule repeatedly, and this is a sound rule. So anything, if the formula was satisfiable from the beginning, anything I derive by the resolution rule should be satisfiable. And the refutation ends when I derive an explicit contradiction, like the empty clause that has no satisfying assignment. Then I proved that the formula is unsatisfiable. So here's the formula from the first slide, 5 clauses. You know, and if you looked at it, maybe you could think about, is it sat or unsat? Well, it's unsatisfiable, and here's a proof of this in resolution. And we can represent, one nice way to think about the proof is just an annotated list. We list the clauses, and for every clause we explain how it was derived. Okay, so the first 5 clauses are axioms, and then maybe I take axioms 2 and 4, and I can resolve them over Z, which occurs positive in clause number 2, negative in clause number 4, to derive X or not Y. Okay? So then I take that clause, and I resolve it with the first clause over Y, which occurs positive in clause number 1, negative in clause number 2. So I resolve them to derive clause number 7, which is a unit clause, it's a clause of size 1, saying that X is true. So far, by resolution, I derived that any satisfying assignment to this formula has to set X to true. This is what this means. By the resolution rule, I sort of derived that any satisfying assignment has to set X to true. Okay? So, but now I look at the axiom clauses 3 and 5, and Z again occurs positive in one, negative in the other, so I can resolve them and derive not X. So now I derive that any satisfying assignment to this formula has to set X to false. So it's already clear that this is a contradiction now, and the final formal step is to just take these 2 unit clauses, X and not X, and resolve them, and now you get the empty clause. So that's a resolution refutation of F. Okay, so this is how the resolution proof system works. And if you want to see the structure of the proof, it's sometimes nice to view it as a graph, where you just have arrows showing that this clause was derived to use this other clause. Okay? And if this DAG happens to be a tree, we talk about tree-like resolution. But in general, you should expect the DAG not to be a tree. I mean, it could be any directed acyclic graph. Okay, so this is resolution. So what are the complexity measures that we care about? Well, the first, the most fundamental complexity measure is the length of proofs, or the size of proofs, the number of clauses in the refutation. And, you know, size is, well, it's the most fundamental measure really in proof complexity, sort of corresponds to time for computational complexity. It also gives you a lower bound on the running time on these conflict-driven closed running solvers. Because in principle, what you could have these solvers do is that they could spit out a resolution proof as they go along. Okay? Not necessarily that they're doing it, but you could hack them to do it. And so it follows that if you have an exponential lower bound on any resolution proof, that means that that implies an exponential lower bound on the running time. And you know that resolution never needs more than exponential size, and there are exponential lower bounds. Okay, so let me tell you about some of these lower bounds, getting now to these benchmarks that are hard for resolution and hence will also be hard for CDCL. Okay, the first and the most classic and most well-studied formula in all of proof complexity is the pigeonhole principle, saying that n plus 1 pigeons don't fit into n holes if every pigeon wants a hole of its own. Except that now we want unsatisfiable CNF formulas, so consistently we'll actually write down CNF formulas saying that impossible things are possible. So here you have a CNF formula saying that indeed every pigeon gets a hole, so PI1 means that pigeon I goes into hole 1 or into hole 2 or into hole n. So it gets a hole, but somehow miraculously for every hole j, it's never the case that 2 pigeons PI and I prime go into the same hole. Okay, so it's not so hard to see that this is an unsatisfiable CNF formula. Now, if you think about it, this is not the only way to encode the pigeonhole principle. When we think about it, we usually think of it as mapping pigeons to holes, and then it would be natural to say, well, a pigeon, there are no fat pigeons. Every pigeon should get one hole, and then it should be satisfied. So pigeon I should not go into hole j and j prime. Okay, and then if you somehow have a heightened sense of fairness, you might require also that, no hole should be left without the pigeon. So that then you could say that every hole gets a pigeon. So there are all of these different flavors. And it turns out that for resolution, all of them are hard. So clearly the sort of the easiest one in some sense, the hardest one to prove lower bounds for is if you throw in all of these axioms. That's what's known as this is the functionality axioms. These are onto axioms, we're onto the holes. So all of these 4 classes of clauses are the onto functional pigeonhole principle. And even that is hard for resolution. So it really tells you that, even if you're giving the resolution sort of strong hints, it really cannot count. Okay, and this is, so this was the landmark, sort of the first result that somehow, I think it's fair to say, got proof complexity started, sort of. I mean, by Haken in 85. Okay, let's look at another example. The handshaking lemma, which says basically that if you have an undirected graph, if you count the vertex degrees in this undirected graph, you will get an even number. Okay, so now we encode this in some kind of sneaky way in the following way. So we say that the variables would be the edges in our formula, and then we somehow label the vertices 0, 1 so that the total sum of all the labels is odd. So for instance, you could just pick one label 1 and all the others 0, that would do. And it's actually without loss of generality. And now we write down small CNF formulas requiring for every vertex that the parity of the number of true edges is equal to the label. So around this vertex, we want to see 1 of x and y true and 1 false. These are these 2 clauses. Whereas around this vertex, we want to see y and z both being true or both being false. Those are these 2 clauses. Okay, so it's sort of clear that I can just take any graph, label it 0, 1, make sure the labeling is odd, and then mechanically generate this formula, right? And if this graph is an expander graph, if it's a very well-connected graph, then this is a hard formula for resolution. Very hard. Okay. So it sort of tells you not only, is it the case that resolution cannot count, it cannot count mod 2 also in a very strong sense. And then, as was already mentioned, another good example of hard formulas is just sample them randomly. Okay, take like n variables, sample randomly 4.5 times n random 3 clauses. That formula will be unsatisfiable with overwhelming probability. It will also be super hard, exponentially hard for resolution. And there are many other. Resolution is sort of by now a fairly well-studied proof system. You can write down things like other NP hard problems, K colorability, independent set, vertex cover. There are some other interesting formulas that I also won't have time to talk about. But the list just goes on and on. So resolution is a fairly well-studied proof system. And I guess it sort of begs the question, well, if all of these formulas are hard now, how can the SAT solvers be so fast, right? And I think there are 2 answers to that. I'm getting a bit ahead of myself. But firstly, somehow, if you're trying to verify a processor circuit design, you don't very often see K colorability instances. That's sort of not what the functionality of the circuit is. So somehow, and also, these combinatorial instances are somehow built to be hard. Whereas if you have these gigantic industrial instances, they're coming from designs that are somehow designed by humans, and somehow they have some structure, and it just somehow seems that the SAT solvers can harness this in some way. And it would be great to make this formal, and people are thinking about whether something can be, something more intelligent, more formal can be said than this sort of hazy, harnessing structure, but it's really very much an open question. So this is that. I don't want to go in that direction. What I want to talk about now is how do you prove these lower bounds? Like roughly how would you prove them? Turns out that you should look not at the size of proofs or the length of proofs, you should look at the width of proofs. Okay, you should look at the size of the clauses in the proofs. Okay, so clearly, how large can a clause be? Well, it can mention every variable at most once. So, it's upper bounded by n. It's also clear that if I tell you, for instance, that, okay, here's a CNF formula, and it's over n variables, and it has a resolution refutation where all clauses have size at most 10, say, okay, then I know that there is a resolution proof in size n to the 10. Simply, how many clauses are there with 10, right? So so an upper bound on width gives you an upper bound on length. And interestingly, it turns out that this counting argument can actually be tight. So there are formulas that somehow, yes, you really need more or less n to the 10 clauses, or at least say n to the 5 clauses. What is interesting for us, and which is much less obvious, is that there's actually a connection in the other direction. If I can prove that in any refutation of a CNF formula, if in any proof of unsatisfiability of a CNF formula, there has to be one wide clause, just one wide clause, then that implies that the formula requires exponential size proofs. So here's the formal statement. It's sort of the parameters you can think about is, say that I manage to prove that the width is linear in the formula size, then I'll have n squared over n, so I'll get n, so I'll be scaling exponentially with n. That's sort of the range of parameters that is most interesting. And it kicks in, but it kicks in already for around square root n times log n. And these days, I mean, this was not how these lower bounds I told you about before, this was not how they were proven, but if you're teaching a course on proof complexity these days, you'll prove them via this width connection. Or at least that's what I would do. Now we talked about this restricted case before of tree-like resolution, where the proof DAGs have a tree-like structure. Then it turns out that there's a stronger bound. You can actually get 2 to the width, not this funky kind of thing. Okay? Whereas, so then the width lower bound kicks in immediately, whereas for general resolution, width up to square root n log n, a priori doesn't say anything. Okay? So a natural question is, well, maybe you can somehow tighten the analysis a bit, but it turns out that you cannot. And there's a very interesting benchmark formula that shows you why you cannot do this. And it's a formula saying that every finite ordered set has a minimal element, except that we negate that. So here we have a, we have an ordering between elements e, I, and ej, as encoded by these variables. And we say that the ordering is antisymmetric and it's transitive, but for every element, there is some other element that is smaller. Okay? This was actually conjectured to be exponentially hard in the 80s. It's a candidate for a really hard formula. You can say, okay, then there's this, okay, do you want your order to be total? You can add totality axioms, really doesn't matter too much. So it was conjectured to be really hard, and if you take some state-of-the-art solvers and run them on this formula, sure enough, you see exponential time behavior, except that it actually has linear size proofs. But this turns out to be one of these formulas that are sort of distinguishing between different sat solvers. There are some very fine details in the parameter setting somewhere deep, deep down inside the algorithm that will sort of tell you whether you find this a linear size algorithm or run for exponential time. Also, okay, so these formulas have wide clauses, but then you can do the standard trick to just convert them to 3CNF. And then it turns out that, so you have very short proofs, but the proofs will have to have fairly large clauses. So you could say somehow intuitively, maybe that's somehow what makes them hard to find. But that's not formal, that's just some kind of hazy intuition.
The symmetric formula,
yes.
the resolution proof also similarly very symmetric, or is it?
The good resolution, what the good resolution proof should do, it sort of says, it isolates one of the elements. It's sort of it's a sort of recursive argument saying, okay, let's find the biggest element, and let's show it out of the set. And then it's sort of and then you reduce it to a formula. Now I have all the other elements left, and clearly, so now I have n minus 1 elements. The set is still ordered, and everybody still have a smaller element. But I found one guy who is just by sort of applying anti-symmetry and transitivity, I found that one guy has to be largest. That I can establish. So I throw that one out. Now I'm down to n minus 1 elements. I repeat the argument again, down to n minus 2, and then when I get down to 2 elements, it's sort of easy to see that. So that's how the argument goes. And the fascinating thing is that resolution can sort of do this.
And it's only linear, not quadratic.
Well, I mean, the formula size is, it has n squared variables and n cubed clauses, right? So this n is the size of the formula. So it's, this n is the little n cubed. Okay, and the formula will have size n cubed.
It's somehow confusing. How can you find the maximal element if you finding minimal one is difficult?
Well, actually, it's not when you find the maximum one. You eliminate one element of consideration.
Yeah.
But it can't be the minimal one.
Yeah, that's probably a better way of saying it. Yeah, I mean, it's not an obvious proof, and it was actually, I mean, it was originally found by a computer, and then sort of a resolution proof was extracted from it. Stallmark found it by using his algorithm, and then he sort of, so there's this famous Stallmark method, and Stallmark ran his method, which was at some point believed to, at least by him, to prove that P is equal to NP. Didn't quite pan out, but he got a great company out of it, Prover Technology. And then he ran his solver on this, and it ran fast. And it's like, whoops, that was unexpected. This is supposed to be exponentially hard, and then, at least what he told me. So then he's sort of, looking at the logs, what is happening, and then realized that actually this reasoning is formalizable in resolution.
But the second proof is independent by that, because they probably did it.
No, that's not independent. They have the Bonnet-Gallese is the width lower bound. So Stallmark is the size upper bound. Bonnet-Gallese is the width lower bound.
They set it in, then they down, up, down too, or no?
I don't think so. I don't think, but I'm not sure, but I don't think so. I think they're certainly citing Stallmark for the upper bound.
The other guy was citing.
Yeah, I don't know. It's okay, I don't know. Anyway, yeah. So okay, good. So there's another measure that if you're doing sat solving care about a lot, and that's memory usage. Actually, it turns out that sort of what, if you want your sat solver to run fast, what you really care about is memory management. That's sort of what will kill you in the end. Okay, so then it's natural to say, can we sort of, study something that measures memory? And the answer is the concept of resolution space, where we're going to count the number of clauses in memory that you need if you want like a self-contained proof on the board, presenting a resolution refutation, and sort of everything is on the board. So you have a good board technique, you never use a lemma that you have erased. That's sort of a resolution space. And I don't have time to go into details. It might not be obvious why this is the right measure. Sort of there are strong reasons why it is the right measure. Though it could be noted that certainly you can measure space in other ways also. I mean, somehow we're now charging only one for every clause, regardless of how large it is. So you could say, well, shouldn't we charge for the size of the clauses also? You can measure that. That will be total space. It's sort of clear for resolution that there won't be a large difference. It's a factor of n somehow, and we don't care too much about that. For other proof systems, it will make more of a difference, though. If we, we'll see if we get there. So anyway, so I want to tell you what clause space is. So if you look at the list, the resolution derivation, at some point in time t, the clause space used is like the clauses that you have already derived before now, but will need to use afterwards, right? Because that means you'd better keep them in memory. So let's illustrate this. So suppose you're at step 7, and now it's nicer to look at the DAG. So you can sort of just see the arrows starting at vertices before 7 and going to 7 or later. So let's see, here they are. So you'd better keep these guys in memory at time step 7. So at time step 7, the space is 5, and then you just measure for every time step what the space is, take the max, that will be the space of your proof. Make sense? Okay, so it turns out that, yes?
In the previous picture, were the axioms included in the set of things, or is it?
Yes, they are, but, yeah, good point, okay, yeah, so I was trying to cheat you, but you won't let me, right? So think of the axioms of, you have them on an input, you have on a read-only tape. So they're for free, but when you need them, you have to copy them to working memory. Okay. Or in fact, you could, if you could, it doesn't matter, you could make them, you could sort of give them for free also, actually. Or just, but so you can think of a Turing machine, you have a read-only tape, we don't count that space. We have a working memory, that's where we count the space. But definitely, I mean, in this case, listing all the axioms right at the beginning is sort of a stupid thing to do. So if you really cared about space, you'd do something different here. Definitely. Yeah. Other questions? Space? No? Okay, so it turns out that the space you need for a formula of size n is actually never more than n. Although this proof that achieves this space bound is of exponential size. Okay? And then there are matching lower bounds. for proven for all of the formulas I talked about before, you get the correct bounds you should. But then a funny thing happens when you start going through these papers and you look at the proofs, they're somehow proving with lower bounds but with minor twists. I mean, the technology is exactly the same, the bounds you get are exactly the same, and people in the area started thinking, this is funny. I mean, whenever we have a with lower bound, we sort of look at it, slightly different classes, and out pops a space lower bound. This is funny. And this looks too good to be just a coincidence, and indeed, there's a beautiful paper saying that width is a lower bound on space. And you can say, wait, what do you mean? I mean, the width is the size of a clause. That's sort of trivially a space lower bound, but note that space counts number of clauses. So this is not a trivial statement. This is saying, if I have a CNF formula where in any proof, for instance, take these ordering principle formulas that we talked about, and you have a cube root n lower bound on width, okay? That tells you that if you actually want to refute this formula, there's no way you can find a resolution proof that does not remember cube root n clauses at the same time. And that's that would follow generically from a with lower bound is a priori, somehow not obvious. To me, at least. But once you know it, then these things that are like really neat and simple proofs for this. So, but that raises the next question, and okay, so space and width always seem to be the same. We get the same, are they somehow, it's the same measure in disguise? And the answer turns out to be no. Because there are formulas for which they're very different, for which the width can be, as good as possible, so constant width, whereas the space is essentially worst case, almost linear, except for a log factor. So I want to tell you about these benchmarks also. Of course, these are my favorite benchmarks. They're known as pebbling formulas. They're my favorite because I spent too much time working on them. So you have a DAG, and you associate a variable with every vertex. And then the formula says that source vertices are true. So you have these unit clauses of size 1, just saying that u, v, and w are true. And then you say the truth propagates through the DAG. So axiom number 4 is just an implication, if you look at it, saying that u and v being true implies that x is true. And then clause number 5 says that v and w being true implies that y is true. And then x and y being true implies that z is true. But then we add a final axiom, a unit axiom, saying that the sink is false. Okay, so again, clearly we have an unsatisfiable formula, and it's clear that you take any DAG, which have some properties that you like, you do this construction, and out pops the CNF formula. And there's an extensive, I don't have time to tell you, but this comes from so-called Pebble games played on these graphs. And there's an extensive literature from the 70s and 80s, and space lower bounds, time-space trade-offs, a lot of wonderful results. And these are sort of things that we'd like to prove in proof complexity also. So you could say, well, if we're really lucky, we take a graph with some nice time-space properties, we do this construction, and maybe we get something that has the same properties in proof complexity. Wouldn't that be great? And it would be great. Unfortunately, it's also false. And the reason you can see this is that these formulas are extremely easy. If you trying to solve them with the SAT solver, it doesn't even get to the sort of resolution phase, because it will just see, oh, these are unit clauses. These I have to set to true. Okay, but then once you did that, these clauses 4, 5, 6 also collapse to unit clauses. So I have to set them to true, and then I immediately get a contradiction with Z. And resolution can sort of do this as well. So the formulas are super easy, so we don't get any good results. But then happily, we're not practitioners, we're theoreticians, so we can obfuscate our formulas. And here's an obfuscation trick that you can do. It's not obvious why you should do it, except that it works. So you take every variable and you substitute it by some Boolean formula of limited arity. Let's do XOR. You could do other also, but XOR is the simplest one. So in this way, if I have a clause, not x or y, I just substitute exclusive ORs for it. Now I don't have a CNF formula, so I have a type mismatch, but I can expand it out in the canonical way, and I get a CNF formula. So this is known as XORification, and if the formulas have bounded width, then there's an exponential blow up, but it's exponential in the width. So if we started with 3 CNF formulas, we're fine. There's a blow up factor of 8, but we can deal with that. And now it turns out that the miracle happens. Now sort of, I'm cheating you a little bit, but everything we sort of know over in the Pebble world in the 70s and 80s turns out to transfer to proof complexity. And in particular, there's this wonderful paper showing that you can do, that space is more efficient than time on Turing machines. That anything you can do in time t, you can do in space t over log t. That is actually a pebbling result. Okay, and that turns out to now carry over to resolution. And give you, and it gives you this separation between space and width. Okay, so that's what's known about these measures in isolation. And the natural question is, if you want to understand, also from an algorithmic perspective, if you're trying to solve a formula, say using a sat solver, then typically you'd like to run fast and use little memory. Okay, so it's a natural question to say, can I optimize two complexity measures simultaneously? So these questions have also been studied for all the pairs of measures we've been talking about. And the first one to be proven was that space and width cannot be optimized simultaneously. So there are formulas that are very simple with respect to space, that have very small width proofs, but if you optimize one of the parameters, you essentially get worst case for the other. Okay, and we also know that there are formulas which have very short proofs, but with somewhat wide clauses. And then you can sort of trim the width down, but then the length blows up exponentially. But in this connection with sat solving, and I guess this is a talk on the interplay between proof complexity and sat solving, what I really care about is length versus space. Is it the case that I can optimize running time and memory consumption at the same time? Because that's what sat solvers do. They're extremely aggressive on space. Like all of these wonderful heuristics that they do, that it's very, very, very important that you optimize space. So what sat solvers do is, I'm digressing a little bit, I guess, but these conflict-driven close learning algorithms, they start with a formula, and then they will learn a lot of new clauses all the time. Sort of, okay, if the formula is satisfiable, then also this clause has to be true, and this clause has to be true, and this clause has to be true. You can think of these learned clauses as sort of being the derived clauses in a resolution refutation. Okay, but in order to run fast, 95% of these clauses at least will be thrown away. So 95% of what you learn has to be thrown away. So that's a fairly aggressive space management policy. And it's a natural question is, could that hurt you actually? Being that aggressive, are there formulas where, okay, if you actually kept these clauses lying around, you'd run way faster, but since you're throwing them away, your running time blows up. It's a natural question, and it would be nice to have a sort of a theoretically, well-founded, proven answer for this. And it turns out that indeed there are such trade-offs. So there are formulas for which there are short refutations, and there are space-efficient resolution refutations. But if you try to optimize space, for instance, then the length can blow up super polynomially or even exponentially. Okay, so what this tells you is that when you're doing your sat solving, be careful when you optimize, because you might be optimizing too much. And the formulas for which you get these are, again, the pebbling formulas are one example for which you get this, because that was shown for pebbling graphs in the 70s and 80s, that you have these kind of strong trade-offs. And now, thanks to this generating the pebbling formulas, doing this XOR substitution trick, we get the same results for resolution. Okay. Another interesting class of formulas is that you can actually look at these Zetin formulas I told you about before, these handshake lemma formulas. And if you define them not on expanders, but on sort of simple graphs, then they exhibit time-space trade-offs. And I wanted to tell you a little bit about this because I think it's sort of neat. And I wanted to give, this is sort of getting into a little bit of technicalities. But not too much. So what we're going to do is we're going to take taking formulas over a long skinny grid. So you should think of it as having few rows, like a logarithmic number of rows and a linear number of columns. And then remember, we want this odd labeling. So we, one vertex labeled 1, all the others 0. And then remember that variables are edges, and that we write down clauses encoding the parity constraints. So for the first vertex, A, we want to see exactly one of A or D true. For the second vertex, we have clauses saying that 0 or 2 of these variables, A, E, and B, should be true. And the same for the next vertex, 0 or 2 out of B, F, and C should be true. And for the last vertex in this first column, C and G should both be true or both be false, and then you continue. And again, it's sort of clear that, we recall that this is indeed gives an unsatisfiable formula because every edge will be counted twice, so there's no way you could end up with an odd total sum. Okay, and now the point is, because we've chosen this particular graphs, you can now be very time efficient and you can be very space efficient, but you cannot be both. So let me just show you. If you want to be time efficient, space efficient, what would you do? Well, you could build a search tree that sort of just divides the graph up in 2 parts. So first, you know that somewhere in this whole graph there is like an odd charge. That's sort of the red part. The odd charge is the unsatisfiable part. So now what you do is, you can think of it building a search tree or having a SAT solver, say, just cutting the graph in 2. Okay? And once you have the assignment to these middle edges, you've disconnected the graph, and the odd charge is going to live either in this component or in this component. And at this point, we can compute in which component it lives. So we just recurse on that component, and what do? Well, we cut it in 2. And now let's say the odd charge lives here, and again, we cut it in 2. And cut it in 2. And in a fairly shallow search tree, setting fairly few variables, we isolate the vertex that is violated, and then we have a violated clause. And it turns out that this is sort of straightforward to turn into a very space-efficient proof. So it's really, if you want to find a space-efficient proof, it's sufficient to just build a shallow decision tree. And I don't have time to argue, but it's not a hard connection. Okay. So this is very space-efficient, but the proof size is exponential in the space usage. Because, the proof will sort of be this whole tree, so it might be fairly shallow, but, it's branching out pretty bad. So it's a large proof. Okay, suppose now that you don't care about space, and instead just want to be like time efficient. What would you do? Well, you can sort of do dynamic programming. These are really just linear constraints, and you can think of every vertex as being an equation, and just sum them up. Okay, start with the first vertex. It says that A plus D is 1, and then you sum with A plus B plus E being 0, and that you sum them up mod 2, and you get B plus D plus E equals 0. And then you take the next vertex, which is B plus C plus F equals 0. You sum again, and you get that C plus D plus E plus F should be 1, and on you go. And this is something you can do because, you'd have to write down the clauses representing these sums, but you can do it. CNFs are, they can represent any Boolean function. And resolution is implicationally complete, so you can certainly carry out these computations inside resolution. The only thing that will happen is that, of course, representing a parity of W variables takes 2 to the W clauses. And how large is W going to be? Well, W is going to be the size of this cut. Okay, and how large was the size of this cut? It was logarithmic with some constant in front of it. So we'll get 2 to some constant times logarithmic. So we're going to get some large polynomial. How large? Well, you decide depending on how many rows compared to how many columns. So this is actually, in the end, okay, and I guess you just keep doing it. Look at all these beautiful figures. A lot of pain doing those as well. So, and here we go. And in the end, you've summed up everything, and then every variable occurred twice exactly on this side. So they all canceled, right? And on the other side, you have all the charges, and that's all. So you get 0 equals 1. So that's what happens. And the size and the space is going to be some polynomial, but it's going to be, some fairly large polynomial. Okay, so this sort of tells you that you can be space efficient, you can be time efficient, and then of course the hard part of this is the lower bound, which I'm not going to tell you about at all, but this is this gives you the intuition like where the time-space trade-off should come from, right? And then, there's a lot of technicalities proving that it's actually is that kind of trade-off, and it's not at all tight. I mean, we lose a lot in the parameters, but it can be shown. Good, so that concludes the survey of resolution. So what I want to do in the remaining time is talk a little bit about CDCL sat solvers and a little bit about how to extend them with algebraic techniques, with geometric techniques, which will bring us to polynomial calculus and Canning planes. Okay, and what I said, and what, as I said, the best modern sat solvers are still based on the DPLL method from the 1960s, and then as Sam remarked, well, there are a lot of smart things added since then. In particular, the one crucial addition in the late 90s is conflict-driven clause learning, which is sort of learning clauses and reusing them. And what happens in terms of proof complexity is, it's easy to understand. You're going from a tree-like proof system to a DAG-like proof system. And that turns out that's exponentially stronger. Okay? And that was sort of clear. I think that was clear for a while, maybe in some sense even before these papers. But then, that's a theoretical thing, and the question is like, how do you make it fly? And then there was a very influential paper by Sharad Malik and some other guys in Princeton just around the turn of the century, where they had a lot of smart heuristics, engineering tricks, and that was sort of, I guess these three papers are sort of arguably the start of the era of modern sat solving. So in particular, this paper was like a factor of 100 improvement over state of the art. So when it came out, like people in the sat community said, give us the source code. This is, you're a factor 100 faster than anybody else. This is just not true. Okay, but it was true. And the main work was done by some master students at Princeton. So, pretty smart guys. And actually, if you have some, combinatorial problem these days, the sat solvers are amazingly good. I mean, if you have a Sudoku problem or something, and you're too tired of it, what you should do, you feed it to solvers like Minisat or Glucose or Ling-a-Ling, and like within 1/100th of a second, they will tell you what the answer is, or some other problem. So they're like really good solvers. So how do they work? What's the DPLL method? Well, the DPLL method is sort of just setting variables to values and simplifying the formula until either you find a satisfying assignment or you find a clause telling you why this assignment didn't work. Okay, so for instance, again, our favorite formula that we're using all along, what the DPLL solver might do, it could set x to 0, then it could set y to 0, and then it realizes that, oops, that is not a good assignment, x or y is now false. Let me try for y instead to set it to true. Okay, and then it says, and now what should I do with z? Let's set it to false. Whoops, that was not a good assignment. Because I'm falsifying this clause, let me try to set z to true instead, but now I'm falsifying this clause. Okay, that's a problem. Turns out that, whatever I do to y, it won't work. Setting x to false was probably a bad idea. Let me try to set x to false instead, okay? That's sort of what it does, and this is a very simplified description, obviously. There are a lot of more components, but this is sort of the main idea. And the point is that if you look at this, this is a resolution proof. Okay. So let me show you that this is a resolution proof. What you do is you just look at the variables you're branching over, okay, and bottom up, you apply resolution steps. And you get a resolution proof. I'm cheating you a little bit, but not too much. This is sort of, you can make this work.
Sure, you are taking tree-like.
In particular, it's even tree-like, yeah. So for DPLL, so this DPLL method like the vanilla DPLL from the 60s, will always give you a tree-like resolution proof. Yes. Yeah. And it holds also when you add this clause learning from the 90s, and then what will happen is that you learn clauses and keep them around, and they will sort of add DAG edges that violate the tree-like structure. So clause learning will sort of add edges maybe from here to here or something. Will destroy the tree structure. So sort of, the DAG of what a SAT solver produces is sort of, morally speaking, it's a big tree with some local violations, more or less. Okay. So again, what complexity measures did we talk about so far? We talked about length, which is at most exponential, and then we talked about width and space, which are at most linear then in the formula size. And we're interested in whether they're somehow related to this conflict-driven close learning proof search or not. And in order to get a meaningful comparison, it's good to, length is up to exponential, width and space is up to linear, so let's take the log of the length and then we can sort of see how they scale. And if you think about it, then it turns out that they're actually increasingly strict hardness measure, because you know that there are formulas for which there are formulas which are hard for space but easy for width, right? And there are formulas that are sort of hard for width, but sort of easy for length. So turning it in the other direction, length might say that some formulas are easy that width says is hard, and width might say that some formulas are easy that space thinks is hard. So it gives sort of a hierarchy of hardness measures. And you can say, are they somehow correlated with actual running time? And length is it's clearly correlated in the sense that it gives a bound on the running time. And there are theoretical results saying that it also gives an upper bound, that you can view CDCL as a proof system, and that it's at least within a polynomial factor of resolution for any formula. This is contradicted by another result saying by Alekhnovich and Zborov, saying that, finding these short proofs should actually be hard, or else this parameterized fixed parameter tractability hierarchy sort of collapses. For width, it's a known heuristic to search for proofs in small width, and there are actually, again, theoretical results saying that if you know that a formula has small width complexity, then the CDCL solver will run fast. And then for space, of course, we know from practice that memory management is a huge concern. So somehow there are cases to be made for all of these measures potentially being relevant for actual performance. And so I did some fairly extensive experiments on this, and sort of the depressing answer was that reality is somehow not complying with theory. If you want to see some nice, clear connections, go look elsewhere because they're not there. But there are some nice things you can see. So I personally doubt these, sort of the SAT community is thinking about these papers from the previous slide saying that CDCL can simulate resolution, and if the small width, then the solvers run fast. If you take the right theory benchmarks, you can run experiments, and these experiments just don't seem to corroborate these results. So somehow these theoretical models are leaving out somehow crucial factors that you would really need to care about.
If you look at the proofs, they're doing some rather strange things, right? So
the main thing that they're doing, they are ignoring, they're assuming that the variable selection heuristic is really good. That's somehow the non-deterministic part. You have to assume that you always choose the right variables. That's one assumption. And the other key assumption is that you may never forget anything that you learn. And as I told you before, like in practice, you forget 95% of what you learn. So never forgetting anything is a very strong assumption. Other than that, the models are, these are very good papers, but...
Oh yeah, of course they're very good papers. No, they're great results. I just meant that if you look at, basically they're saying so you give a general resolution proof, you can simulate it with the right choices.
Yeah.
But it's really, it's not getting at the heart of the matter of why CDCL works so well. CDCL works so well for some reason we don't know.
Yeah.
But nonetheless, it's because it's somehow always guided back to the correct thing or something like that by the learning process. We don't really understand why.
Yeah. No, I agree. I mean,
You have to exactly follow this particular resolution group. It doesn't seem to model why we think CDCL is good.
I agree. Yeah. Yeah. And in fact, one thing you can do, I mean, these setting formulas I told you about before on long, skinny grids, in some sense, you set the parameters right, they are easy for resolution. You can even set the parameters so you get linear size proofs. Okay, and then you could say, well, if you believe in these papers now, you know, linear size proof, constant width, there's no excuse not for running fast. Okay, now let's run the best SAT solvers on these formulas. What happens? Okay, this is something that we're looking at right now. SAT solvers are not doing great. They're really struggling. So, yeah. But I mean, these papers still tell you something, sort of. I mean, they tell you that, sort of morally what they tell you is, okay, if you really get your variable selection heuristic right, and if you really somehow manage to remember the clauses that you really need, then you're as good as resolution, right? But those are two sort of strong assumptions. Yeah, and as I said, but also, I mean, the results I've been telling you about are also should be stressed. These are theory results, right? These strong trade-offs are these, well, for large enough n, there is an epsilon and a delta such that you see these very strong trade-offs. These are asymptotic statements. And you can say, well, you know, can you scale them down to something meaningful in practice with something for like 1,000 variables where you can actually see a trade-off? And then you can't take the formulas I showed you quite off the shelf. It won't work. Yeah, so this is not quite updated. This is something that we are doing now, looking into these trade-offs. But it actually seems that these kind of trade-off benchmark formulas that you can prove theoretical results for, they somewhat transfer to practice. So you can actually exhibit, and this is something that I think the SAT solving guys haven't seen before, like, you know, concrete formulas that you can give them where you can say, okay, you choose. Do you want to run fast or do you want to optimize space? But you can't do both. They somehow were living under the assumption that, well, you know, it won't be a problem. And now we can sort of exhibit formulas to them where we say, well, you know, for this one, you do have a problem. In theory and in practice. So I think this is, yeah, so I guess the message of this slide is just saying that if you sort of know what the SAT solvers are doing and you know your proof complexity, there are a lot of interesting questions at the intersection where you can sort of, you know, where SAT solving people will say, for instance, these clause variable selection heuristics. Is this something we can talk about in proof complexity somehow, you know, say something, could we start modeling it in some way? Clearly, it's a very important question. And also these benchmarks that we have on the theory side, can they somehow tell us something about, you know, what SAT solvers do and how their heuristics would need to be improved. Because, you know, you're not solving this formula, it has a very short proof. Is there some fix that you could do to your heuristics so that you remain as good as before on other benchmarks, but you can also deal with this one? And there are, yeah, lots of nice questions to work on. Yeah, I sort of think I covered most of this. Okay, slide, but I could say quickly that, yeah, I mean, you do see strange things sometimes when you run SAT solvers on these theoretical benchmarks, that sometimes you can show that the heuristic sort of goes wrong. Sometimes formulas that look very easy in theory are very hard in practice. And sometimes, for instance, for these ordering principle formulas, there are some very fine, low-level detailed settings in the SAT solver that nobody suspected was that important, and it turns out to be really important, and we still don't really understand why. Okay, so that ends resolution, my discussion of resolution and CDCL SAT solving. So in the remaining time, I want to tell you a little bit about algebraic proof systems, algebraic reasoning, and about geometric proof systems and reasoning. So let's talk about polynomials, polynomial calculus. What you do now is you take your clauses of your formula and you translate them to multilinear polynomials. So you have variables x and bar x, which are formally distinct variables. Let's think of 0 being true and 1 being false. So let's flip true and false for now, because it's sort of natural in an algebraic setting to do that. Okay, so now a clause x or y or not z just gets translated to a monomial x times y times z bar. And the clause being true means this monomial evaluating to 0, and clearly it evaluates to 0 if one of these guys in it evaluates to 0. Okay, so that's the semantics. So for a CNF formula, you now get a bunch of polynomials, and now you have derivation rules. So you only want to consider, you can be over any field, so pick your favorite field. In practice, this would always be F2, GF2. In theory, you know, pick any field, finite characteristic, maybe even characteristic 0. And so, but we always want to be Boolean, so we have axioms saying that x squared minus x is always 0. We have axioms saying that we respect the meaning of negation, so x and x bar should always take opposite values. And then what we can do is we can take linear combinations and we can multiply by variables. Okay? And now showing that a CNF formula is unsatisfiable is the same thing as deriving that 1 equals 0 in this field. Okay? And this is an if and only if. Meaning you can do it if the formula is unsatisfiable, and clearly, you know, if you can do it, then clearly the formula is unsatisfiable. Okay, so good. So now we have polynomial calculus. What are our complexity measures? Well, clauses that we had in resolution, we saw they turn into monomials. So in resolution, we were always counting clauses, so it's natural now always to count monomials. So let's write out all our polynomials as sums of monomials, and now we're going to count monomials. So then size is just the total number of monomials in a proof or in a refutation. The width of a clause will turn into the degree of a monomial, right? So width now sort of corresponds to degree, and space, before we were counting number of clauses, now we'll count number of monomials in memory. Okay? So sort of all the definitions are exactly the same, except you count monomials instead of clauses. The one difference is that in resolution I was sort of saying space, length, size or length, and I didn't really care. Turns out that now in polynomial calculus we should care, because you know, the number of derivation steps, that's the length, but the point is that polynomials can have exponential size, and this does make a lot of difference. If you don't care about the size, then there are very short proofs, but the polynomials in the proofs are exponential size. So in the context of polynomial calculus, size is really the measure you should care about, and length is somehow not so interesting. So it's not hard to show that polynomial calculus can do anything that resolution can do. So you can just mimic resolution step by step. In the interest of time, you know, I have the simulation on the slide. I think I'll skip it. It's just an easy exercise. So that means that any upper bounds you have for resolution carry over to polynomial calculus. It's also strictly stronger because it can do things that resolution cannot do. For instance, these Satin formulas, these handshaking lemmas, if you're over GF2, you know, you sort of get parity reasoning for free from the fields, so Satin formulas are easy. Also, onto functional pigeonhole principle formulas are easy. This pigeonhole principle where you have said that every pigeon goes into exactly one hole and every hole gets exactly one pigeon, that's actually an easy formula, it turns out, for polynomial calculus. So polynomial calculus can be strictly stronger with respect to size and degree compared to resolution. For space, annoyingly, we don't know. It seems reasonable that there should be something, you know, you should be able to be more space efficient if you use polynomials, but we really don't know. It's a great open question. Then it's sort of a general pattern for polynomial calculus is that many other of the things we know for resolution carry over with little or no modification to polynomial calculus. So again, you know, for resolution we know that if you have a width upper bound, that implies a size upper bound. Same thing holds for polynomial calculus. A strong width lower bound implies a strong size lower bound in resolution. Same thing for polynomial calculus. These connections are exactly the same as for resolution. They're optimal for the same reason. The benchmarks are the same. And in particular, so if you want to prove size lower bounds, just as for resolution, I said if you want to prove length lower bounds for resolution, then study width. For polynomial calculus, if you want to prove size lower bounds, then study degree. Okay, and the one difference is now that while for resolution we really know fairly well how to prove with lower bounds, for polynomial calculus proving degree lower bounds is like a real challenge. That's really hard.
And when you're talking about the lower bound, you're talking about some field or every field?
Good. Depends on the result. Sometimes, okay, so typically you have two flavors of, typically there are some benchmarks that hold, lower bounds hold for any field except a field with bad characteristic for you, and then there are some other results that hold regardless of field. And when you're looking at different fields, typically there are GF2 is like in some sense the hardest field to deal with. Characteristic 2 is hard if you want to prove lower bound. So what do we know? What formulas are hard? Well, Pigeonhole principle is hard. The vanilla version is hard. And also if you throw in functionality axioms, it's still hard. So, but functionality plus onto axioms, then it's easy. But if you just remove these, you know, if you just don't require that the pigeon mapping is functional and onto, then it's still hard. These Satin formulas, parity reasoning is sort of hard if it is not supported by the underlying field, sort of, more or less. I mean, that's a result by you, right? So you think it's sort of reasonable to say that, you know, it's counting mod P is sort of hard if your field has characteristic Q, and P and Q are different. Random KCNF formulas, that's an interesting case where like it was proven that random KCNF formulas are hard in all fields except in characteristic 2. Okay, and then proving that you can do it also in characteristic 2 was like a major pain. This is a deep paper. Space is also tricky. I mean, I said we cannot separate resolution space from polynomial calculus space, although we would like to do it. And even proving space lower bound was tricky. And this is the one place where you really care about whether you have unbounded width or 3CNF formulas. Proving space lower bounds for unbounded width is not too hard. But then getting it for KCNFs turned out to be, there's a long sequence of work where you got it for some very unnatural 4CNF formulas. Then a beautiful paper got it for random 4CNF formulas. Then for Satin formulas, these, again, handshaking lemma on some 4 regular expanders. 4 regular means, again, it's a 4CNF, but there was a major barrier getting down to 3CNF. So we had nothing for 3CNFs. And then finally, like last year, we got proved that random 3CNFs are hard with respect to polynomial calculus space. But we still don't know. It should be, if you take any 3 regular expander and you define a Satin formula on it, it should still be hard for polynomial calculus space. But we don't know, we don't have that for any 3 regular graph. Also, if you take the Pigeonhole principle and you turn it into 3NF by just these standard extension variables, right? You take these wide clauses and you just split them up into chunks of size 3. Okay, then all the lower bounds we have crash and burn. And we don't know anything. So, you know, a priori, it's consistent with state of the art that the Pigeonhole principle is super hard with respect to space, but if you're given the 3CNF version, then you can do it in constant space. We can't rule that out.
In general, if you just take any formula for which resolution is high, and you replicate a variable twice, put an axiom saying 2 of them are equal, use the main time?
I think it's hard to claim something general. I mean, resolution, at least for this turning things into 3CNF or not, resolution is generally sort of well behaved. I think it's fair to say. Somehow, or at least I don't know of any result where it's like really a problem whether you have the 3CNF version or the wide version. But for polynomial calculus, it's sort of it makes a difference. It somehow breaks our techniques for some reason that I really don't understand.
What about the Pigeonhole principle where instead of having all n squared possible edges, you have a expander graph, a D regular expander graph?
As long as D is 4, at least, then you're good. Okay. You can do it for 4, yeah.
You can do what means it's hard or easy for?
No, it's hard. It's what it should be. It's hard. Yeah. Okay. This follows from this is from this paper also. Okay. Can do it. Yeah, from the same technique. So for resolution, we knew that width is a lower bound on space. It's a great question whether the same thing holds for polynomial calculus. We don't know. And there's also, for resolution, we can separate width and space. We know that there are formulas that have very small width, require very small width, but you can do in large, but requires large space. We sort of have the same for polynomial calculus, but that's a result that depends on the characteristic of the field, which is very annoying. So you'd like to get a space degree separation that is independent of the field, and this we don't know how to do. And sort of with respect to trade-offs, the same kind of results hold as for resolution. Yeah, so let's see if we ever get to cutting planes or not. So what about algebraic sat solving? Well, it turns out there's sort of the theoretical potential is there, right? They should be exponentially stronger, but somehow it just seems hard to do it. So there are no really good algebraic sat solvers that can compete with state of the art. Yeah, and I don't know, I mean, it's a good question. Is that because it's just harder, or is it just because people have been working on resolution-based method for 50 years and haven't really been working on algebra methods? Maybe it's both, we don't know. Yeah, so I think in the interest of time, we'll just jump over cutting planes. And the short summary of cutting planes, I can sort of tell you, well, I can tell you what it is. Again, you just translate your clauses x or y or not z. Now it gets translated to a linear inequality, and you just can do the natural reasoning with linear inequalities to derive that 0 is greater than 1. And the summary of cutting planes is, we know some things, but it's really, most of the questions we really care about are open. That's a 1-minute summary about cutting planes. There are a number of very good open questions there. And also but for cutting planes, people are actually working on sat solvers, trying to build so-called pseudo-Boolean sat solvers. There's an active community working on this, whereas on algebraic sat solvers, I don't know of any active community. And the limitations they are running into, it's sort of very clear when you start looking at what their algorithms are doing, that you can see, okay, what makes cutting planes really stronger than resolution? Okay, like where does it shine? And somehow their algorithms are searching for a too narrow subspace of cutting planes to give the algorithms the opportunity to shine. And this is something that, again, sort of coming with a theoretician's glasses, you can sort of see, but if you do this, you will be essentially doing only resolution. And this is something that they maybe hadn't realized. But there are a number of interesting questions, algorithmic questions, like could you algorithmically harness the power of cutting planes? So, summing up, what I tried to do in this talk, we talked a lot about resolution and also a fair amount of polynomial calculus. We talked very briefly about cutting planes, but at least I mentioned it. Resolution is fairly well understood. It is also a basis of very successful sat solvers. Polynomial calculus, still reasonably well understood, but the number of nice open questions. Most of the picture that we have, it sort of looks roughly like resolution, but with some twists. But there are a number of things that we know for resolution that we suspect for polynomial calculus, but are not able to prove. Cutting planes is pretty much a big mystery. Some lower bounds, but most of the questions we care about are wide open. And these are like long-standing open questions, like things like proving that, for cutting planes, somehow with linear inequalities, it should be hard to do parity reasoning. The handshaking lemma should be hard. Stating formulas should be hard. We don't know how to prove that. There are some conditional results. Random KCNF formulas definitely should be hard. I mean, random KCNF formulas should be hard for anything. Again, that would be like a major achievement to prove anything for cutting planes. And there are some nice problems that sort of arise when you start looking at sat solving. All of these complexity results that we have, can they somehow inform our algorithmic thinking? And the main challenge that I see and that I'm sort of working on in the applied part of my research is Okay, you know, resolution-based sat solving, the methods are essentially from the 60s. Why can't we use algebraic techniques? Why can't we use geometric techniques to get better sat solvers than the solvers we have today? Are there really fundamental barriers here? Or is it just that we need to, you know, work as hard as the people have been doing on resolution-based solvers for the last 50 years? Okay, thanks.
Questions already about example with calculation.
I have one, okay? So you have these formulas, difficult classes of difficult formulas,
Yes.
different classes of difficult formulas for resolutions. Is there some kind of reduction classification that some formulas are easier than others? It should, it would be natural to have something like this, like everywhere.
The short answer is it's a good question. I don't really know. I mean, mostly what the results will look like is you will have these, like either it's easy. Actually, sort of most natural benchmarks that you study in resolution, I think it's fair to say that either they're like super easy, so they have linear sized proofs, or they're exponentially hard. I mean, and then you can get artificial benchmarks by sort of padding arguments, but I think it's reasonably fair to say that for most sort of natural benchmarks in the literature, they either have like very short proofs, or they're super polynomial or even exponentially hard. I mean, it's, to the best of my knowledge, like coming up with a natural combinatorial benchmark, for instance, that has complexity n to the 10, say. That's typically, you don't see those somehow.
Yeah, but for example, there are classes, you know, if we are looking for contradiction in something, often like Gröbner, lemma, and Brouwer-Fix point, you often reduce one to other.
Yes.
So it doesn't translate this kind of reduction, which are probably known for algorithmic classes. Do they translate in something for
I mean, you can do, I mean, you can prove some results by reducing like a formula to another, right? I don't know if that's, but I don't know of any like real classification as such. It's more like sometimes you could reduce, you can do things like, okay, I know that this formula family is hard, and then what about this formula family that I don't know? Then you can prove results along the lines of, well, sort of from this formula, resolution could sort of, you know, do the reduction from this problem to this problem can in some moral sense be carried out inside resolution. And hence, since this, you know, problem, or wait, the reduction from here to here could be done inside resolution. And so you're reducing from a hard problem, the reduction can sort of be carried out inside resolution. Hence, the resolution lower bound must also apply to this other formula family. I think there are some results along these lines, but not.
This is the thing, because to get difficult formulas, you start not from you start from something like Pigeonhole principles, when there is a short proof in natural mathematics.
Yeah.
So you don't start with a difficult, and you complete something and try to. You start with something which is relatively easy if you have more proof techniques.
Right. Yeah. But it's, I mean, it's also interesting. I mean, the reason to study it's also interesting to understand not only that some things are hard, but which things are hard. I mean, it's really informative if you want to understand what resolution is. Like what the Pigeonhole principle lower bound really says is morally somehow that any formula you have where you need to do counting will in some sense be hard for you. That's sort of morally what the Pigeonhole principle lower bound says. And that's already, I mean, that's an interesting result on the limitation of the proof system, which I think is informative. So yeah, it's a good, I think the answer was, the question was probably better than the answer, I'm afraid. But,
another question. So in sort of graph theory and optimization, there are some parameters associated with graphs, like free weights, and which tends to try to be positive news. So one is bound in the free weight,
Typically, yeah, I mean, you could typically, if you're interested in it, then yeah, typically if you set up your parameters in the right way, if the tree with the smalls, then the formula will be easy, yeah. Those kind of things will hold. I mean, the fixed parameter tractability community is pushing this explanation, right? There's this theory saying that, okay, why are instances easy? Well, you can say there are these islands of tractability, like, Horn-sat formulas, 2-sat formulas, some small tree width formulas or something. And now you get some instance out there in the wild, right? And the reason, so why is the sat solver so successful? Well, the explanation is supposedly that you may not live on an island, but you're really close, so you can swim there. You just set a few variables in the right way, and now you reach the island, and from there it's, then you're safe. This is a very sort of pleasing and attractive explanation to me. I mean, it looks really nice. The only problem is I don't believe in it. I don't believe that that's a sort of a reasonable description of what is actually happening in practice. But certainly, I mean, there are, I would say that line of research would be, one of the most glaring examples, perhaps, of, what I totally skipped in this survey. There's certainly a lot of nice research on that.